Hello, we are Team BTEMS from INA University, and today I will present about the modeling of electric vehicle summer management system. Our team thought about how to reduce the power used for summer management in electric vehicles. This is the table of contents. Next, I will talk about the research background and the need for research. Since the electric vehicle market has grown so large today, it is important to develop electric vehicles with long mileage. However, there is a problem that electric vehicles consume a lot of electricity when heating on a cold day, so the mileage is greatly reduced. In addition, most of the preceding studies focus on reducing the loss related to the traction of electric vehicles, and no research has been conducted on electric vehicle summer management. Therefore, research is needed to reduce the power used for electric vehicle summer management. The following are the research goals and contents. This study aims to analyze the simscape case of Tesla Model S provided by MathWorks and build on it to create an improved loop that achieves efficient summer management of EVs. Next, I will talk about the research process. This is an analysis of the coolant flow in an electric vehicle on a cold day. The coolant from the inverter flows without passing through the radiator and gets heat from the heater to heat the battery. This loop continues to circulate. The battery used here consists of 20 cells connected in parallel mode to form a module. 4 modules are configuring the battery pack with a serial mode. The coolant flows from port A to port B and heat exchange occurs with the battery via the coolant jacket. Cooling or heating occurs during this process, and the temperature of the battery can be checked by subsystems such as S1, S2, S3, and S4 installed in each battery module. The following is an analysis of PTC, an important heating device for EV summer management. When the environmental temperature is lower than the set point and the moist air temperature is lower than 35 degrees, the PTC heater operates to heat the moist air. Next, this is about battery heaters. The heater transfers heat to the coolant that enters the battery. If the environmental temperature is less than 5 degrees, the heater turns on and off depending on the temperature of the coolant entering the battery. This is about the loop that we improved. The first loop reduces power consumption by reducing the use of PTC heaters on cold days. The changes in the improvement loop are as follows. First, the condition of the three-way valve is modified so that coolant flows to the radiator when the battery temperature is above 28 degrees. Second, a heat exchanger is added between the moist air and the coolant. Finally, a three-way valve was added to control the flow of coolant into the heat exchanger. In the improved loop, if there is a heat exchange between the coolant and the moist air, the coolant flow is as follows. At this time, the moist air is heated by receiving heat from the coolant. Comparing the temperature of the moist air entering the PTC heater through the graph, it can be seen that it is 23 degrees. Which is 2 degrees higher than the existing loop. The result of plotting the operation time of the radiator and the PTC heater is as follows. First, the reduction in the operation time of the radiator means that the amount of waste heat available has increased. And second, the reduction in the operation time of the PTC heater means that the amount of power used to heat the cabin has decreased. The second improved loop is to stabilize the heat flow through the heater. We are checking the correlation between the heater and the heat flow rate. In addition, we found a bounce phenomenon in which the heater is quickly turned on-off. In this case, electrical power may be wasted during the on-off process of the heater. So, to solve this problem, we are added the three-way valves and heater pump. When the environmental temperature is minus 10 degrees, the circuit is designed to blow the coolant as shown in the figure. As a result, you can see the debouncing heat flow scope as shown. And you can see that the temperature is also stable. Finally, the heater on-off bouncing phenomenon has been resolved. So, this result causes minimized electrical power consumption while using the heater. Through these studies, we expect the improved coolant loop to reduce the power used for electric vehicle thermal management, increasing vehicle mileage and overall efficiency. Thank you for listening.